So write the redox equation for the following galvanic cell. Again, we're using that example from the first slide, being consistent here. So the zinc was the anode, which comes first. It's going from a neutral charge to a positive charge as oxidation happens. So we can write the half reaction and balance it with 2 electrons. Our cathode is copper. Again, we go from copper 2+, because we're being reduced, it'll go down to copper solid. And we have to add 2 electrons again. Our electrons already balance out. 2 cancels with 2. So we don't need to do anything with a multiplier here. We can just combine them, reactant side to reactant side, product side to product side. So we get zinc solid plus copper ions goes to zinc ions plus copper solid. This was a pretty simple example. We're going to try that other example that we had for cell notation next. Our more complicated example. Write the redox equation for the following galvanic cell. We are representing that same cell with chlorine gas and iron that we had previously as our example for cell notation in the previous presentation. So let's take a look at this. We know that the electrodes are on the outside. So in this case, they are platinum. Those are our electrodes. If we look at our cell notation guidelines, the third one tells us which side is the anode and which side is the cathode. So our chlorine is the anode, and our iron side is the cathode. Which hopefully we can read. Okay, so our chlorine gas then is being oxidized, anode oxidation, and our iron is being reduced. It's at the cathode reduction. Platinum is the electrode. It is not part of the redox conjugate pair. But let's say we didn't know that from having heard about that in the other presentation. Well, if that is the case, the redox conjugate pair will always contain the same metal cation or the same anion. In other words, we have chlorine for both species in our anode on this one, and that is an anion, and we have iron in both species in our cathode, which is the metal cation example. Platinum is neither chlorine nor iron, so it is not part of either conjugate pair. Hopefully that will make it obvious. When we pull the redox conjugate pair, our first impulse may be to put chlorine gas on the reactant side and chlorine on the product side, because that's the order that they come in the half cell. Our first impulse would be incorrect. Oxidation makes the oxidation number more positive, so we want the chlorine on the reactant side, the chloride on the reactant side and the chlorine on the product side. We balance for mass by putting 2 chloride ions, and then we balance for charge with 2 electrons. Now our other half reaction is going to include the iron. And again, we might want to put Fe2+ on the reactant side and Fe3+ on the product side, but at the cathode we have reduction, which is going to reduce charge. So we want instead the iron 3+ going to iron 2+. And when we do that, we balance it by adding an electron on the reactant side, and then when we go to recombine the equations, we have to multiply by 2 so that the electrons will cancel out. Our balanced equation then for this reaction is 2 chloride ions plus 2 Fe3+ ions, making chlorine gas and 2 Fe2+ ions. Now, what was the purpose of that platinum again? And does it need to be part of the redox equation? Because it seems kind of weird that it's in cell notation, but it's not in the balanced redox equation. And the answer to that is they were the electrodes. The electrode is not part of the reaction, so we don't include it in the redox equation. But the electrode is important to the galvanic cell because it's going to carry our electrons from one side to the other. anytime you have two aqueous elements, or when we have one gas and one aqueous element in a half cell, we will have an electrode that is not part of the redox equation. Anytime. Let's go the other way. What about when we go from a redox equation to cell notation? So write the following in cell notation, and we have copper and silver as our pairs. We have solids on both sides. Those are our electrodes. Copper is going from an oxidation number of 0 to 2+. And when we increase our charge, we are talking about oxidation. That is our anode, which means that silver is our cathode. So we're going to put copper. We're going to have a line. We're going to have our copper ion. We will have two lines representing the salt bridge. Then we will have silver, one line, and then silver solid, because that is our electrode. That was a relatively simple example. Let's try something more complicated. Write the following in cell notation. We are given a balanced redox equation. That was nice of us. We want to identify the oxidation and reduction so we know which side comes first in cell notation. So we have chromium with a 3+. That is the oxidation number. And then over here, our chromium has 14 from oxygen, minus 2 gives us 12. 12 divided by 2 gives us 6+. So the oxidation number here is 6+. Okay, so if we're going from 3+ to 6+, we are talking about the anode. And that means that bromine is the cathode. So we're going from bromine 2, which is a 0, to bromine minus, which is a -1. And yay, that's great. You wanted to know those things. That's wonderful. But what else do we need to do? What else is going on here? So the second thing we notice is that the reactants and products are all liquid or aqueous phase. We don't have a solid amongst them, but our electrodes need to be conducting and solids. So what are our choices? We could use platinum, silver, or palladium. I am going to choose platinum, just for the hell of it. Also, we've used it before. Okay, so on the outside of my cell notation, I'm going to have platinum on both sides. And finally, we need to know what our redox conjugate pairs are, so we can break the combined equation into half reactions. Opposite of what we normally do. All right, so we've got our chromium, and I pulled the stuff that goes with the chromium, right? I have oxygen in my dichromate, so I need to have water, and I've got H+ on the other side because of that, and then I've got 6 electrons to balance out the charge. I can do the bromine pretty easily because it's just bromine liquid going to bromide ion. And again, I have 6 electrons to balance the charge. It makes sense that this would be balanced to begin with because it was a balanced redox equation in the first place, so it should be balanced as a half reaction for overall charge. Okay, now when we put this into cell notation, and this is important, we are going to include H+ or OH-, but we leave the water out. And right now, your brain may be going, what? Why am I leaving water out? Remember that thing where we said that chemists like to simplify things as much as possible? If we have 2 aqueous components, we know that water already is there. But we don't know if we're in acidic or basic solutions. So we have to include the H+ or the OH-. It is not part of the redox conjugate pair, but it's necessary for understanding what's happening in that redox reaction. So when we write our final cell notation, we have our 2 platinum electrodes on the outside, on both sides, because everything's aqueous or liquid. Our chromium half reaction includes chromium 3+, the dichromate, and the H+, because we have to indicate that we're in acidic solution. It does not include the water, because that is assumed. It is assumed when we have an aqueous solution. On the other side, we have our bromide ion and our bromine gas. I will say, I did not include the fact that these are aqueous. I just assumed you would know because you can't have dichromates with 2- charge unless it's dissolved in water. This is a chemist thing to do. Simplify it and assume that everybody knows what you're talking about. We are guilty. All right, let's summarize what we learned. When we're going from cell notation to redox equations, we're going to identify your oxidation and reduction redox pairs, exclude the electrodes that are not part of the redox pair. We're going to balance the half reactions like normal, but we make sure the species represent the correct type of oxidation or reduction. So in other words, make sure that your oxidation is going up in charge and your reduction is going down in charge, or you have put them backwards. And when you recombine your half reactions, balance your overall charge. When you go from redox equations to cell notation, put electrodes on the outside, and that may be a solid species that is part of the redox pair, or it may be something else like platinum, palladium, or gold. Make sure you follow the other rules in the yellow box there, and include H+ or OH-, but leave out water. Always leave out water, because we're chemists and we like to simplify things, which is confusing unless you know why. Okay, hopefully that is enough that we will be able to do this with confidence when we get to class.